So today we're going to talk about multivariate data analysis for NIR data. Okay, so what exactly is our motivation for doing multivariate analysis on spectroscopic data? So as you probably all know, you've probably dealt with spectroscopic data in the past. It is multivariate by nature. You have many, many wavelengths that you're looking at. And spectroscopy gives us valuable insights into our chemical nature and the composition of different sample types, and it can also give us physical characteristics that are specific to the samples. Again, like I said, they are highly multivariate by nature and require very powerful analytical tools to unlock that information. And most especially, multivariate data analysis is used for near IR, and that's due to all the overtones and combination bands that you see in the NIR, so you tend to not have your nice sharp peaks that you might have in, say, the mid-infrared or your Raman data. So there's a lot of applications for near IR and spectroscopy in general. In the pharma world, we can do real-time blend uniformity. You can identify raw materials that are coming in. You can also look at process data, just for example, on to identify where your failures are coming from, some root cause analysis. Track oil density before shipment, classify jet fuels. So there's a lot of interesting things that you can do for process monitoring as well as quality assurance to make sure that you have the right amount of whatever constituent you're interested in, or a low enough amount. So near IR is often used for measuring moisture in a lot of things to make sure that your moisture isn't out of control. So let's talk just real quick about where NIR is. So this is the electromagnetic spectrum. And as you see, we have our near infrared is between 720 and 2500 nanometers. In wave numbers, that is about 4,000 wave numbers to 13,000 wave numbers. We tend to go back and forth in the near infrared depending on which scheme people are used to working in, whether it's visible or mid-infrared. All right, so some of the benefits of using near IR is it is non-destructive. You don't have to really do much sample preparation, if any. It's very easy to integrate into your process, and it contains both chemical and physical information. Now, the challenges are that these spectral features are very broad and undefined. That's due, again, to those overtones and combination bands, and so you can have a lot of different things that are happening that look very similar from the outside, right? You also have some serious issues with scattering effects because the wavelengths are so small. It causes a lot more scattering because your ratio between your particle size and your wavelengths are closer. So often, almost always, you require multivariate data analysis to really understand your NIR spectra because you have all these overlapping bands. You often get a very broad band that may have individual bands underneath it to pull out your information. We can do any sort of multivariate data analysis on our spectroscopic data, just like any sort of process data. We can do exploratory analysis and classification using principal components analysis, maybe LDA or SIMCA. And we can also get quantitative analysis out of it with our spectra and reference data. And then we can get regression models as well for future predictions. This is really good because it can replace expensive or destructive testing. And the analysis actually happens in seconds, not hours. If you have to do an HPLC on a pharmaceutical tablet, for example, that's going to take hours for each individual sample, and then you have multiple samples, so you might take weeks to be able to get your information back. And it also reveals the true structure of the data. It allows you to see everything that's going on at once rather than just focusing on one particular component. So one of the things that we always tell you, and this is especially true with spectroscopic data, is to visualize before you analyze. You don't want to just look at your spreadsheets, you kind of get overwhelmed with that. But if we just do some simple visualizations like a line plot, you can tell very quickly if you have a poor scan. Maybe you had a sample that was not in the holder correctly or just something wrong. You might want to pull that out. You can see if there's highly noisy data. It gives you some cues on how you're actually going to want to pre-process your data, because you often need to pre-process in NIR especially. So another thing that we also like to do, and I'll give some examples of this later, is descriptive statistics. This gives us an overall view, a map of what's going on with the spectra to show the areas that has the highest variation. And by looking at different things, you can determine whether it's due to sampling or it's due to chemistry effects or particle size. And again, this is a tool that you're going to use in order to determine what sort of pre-processing you might want to do. If you're looking at a reaction, sometimes it's really interesting to look at a matrix plot. This puts all of the spectra kind of in a three-dimensional array, so you can see how things are changing as you look through the samples. This isn't the best example of this. This kind of looks all the same. But if you perhaps had a reaction going on, you might see this region increasing, or the region on the right increasing as you're going through the samples, while you're seeing the region on the left decreasing as you go through the samples. So you can see how there's some interaction between variables, and this is just by general plotting. Okay. Now, so let's quickly talk about principal component analysis. This is going to be our exploratory analysis. You get your original data, you break it down into the most variations. So the first thing you do is mean center your data. We're going to take out the average spectrum, otherwise the direction of the most change is towards that average spectrum. Your first principal component is going to be the wavelength ranges that are the highest contributor to the variation that is happening in your data. And then the principal component 2 are your next highest contributors, and so on until you start to look like noise. Now, these loadings contain your spectral features, and they should look something like your original spectra, and you should be able to interpret them, right? If you start getting to the point where it looks very noisy, it's probably noise and you want to stop and not evaluate any further. Okay. The individual loadings, keep in mind, are not necessarily corresponding to physical constituents. It could be chemical changes, it could be some other things going on. But because if you look at them in this way, you can very quickly tell when your noise is going to be seen. We always want to take a look at the scores. Just like in any other data, we want our scores to kind of be symmetrically distributed, and you use it to look for samples, relationships between samples like groups or outliers. Different things that we might do with spectroscopic data is you might monitor a time-evolving process, chemical reactions or drying or chromatographic elutions. It will follow a particular space or a path in the score space. And so you can start to see if your batches are consistently following the same path, and you can determine an endpoint by that route as well. This is just another slide explaining when we get to the point of we're looking at different components. When the loading vector starts to look like noise, there's no more real information. Okay, and always look at the % explained variance for the component with respect to the objective of the experiment. This is just a quick overview again of a loadings plot. We look at our loadings and our scores together so that we can see which spectral ranges are causing the separation between different things. So in this case, we're looking at some different oils. We've got olive oil, corn oil, safflower oil, and corn margarine. And what we see is in principal component 2 is what separates out corn margarine from the rest of the oils. And when we look back at our loadings, we can see very clearly there's this one peak around 954. That's very high, and that's contributing to what's different between those. And in this case, it's a peak that shows up when you heat treat and cause a trans reaction, or trans fats show up. So one of the most common questions I get asked when people call me is, how do I pre-process my data? And it really comes down to a lot of what you know about your situation. One thing you need to keep in mind is what information you're trying to get out of your data. That's very important when you're going in, but also your sample handling. So you want to understand what you're actually doing with your samples, why you're getting the output that you are getting, so that you can determine what pre-processings would make the most sense. So there's different types of ways that we can collect spectral data. We can do a simple transmission. You have your light source, it goes through your sample, it disperses out onto a detector, and so we get a transmittance. The transmittance is, of course, related to absorbance, which is then related to your concentration. And these things are wavelength dependent. We can also do diffuse transmission. This is somewhat common in the pharmaceutical world. You might do transmission through a tablet, for example. You lose a lot of your intensity through backscatter. And then when you're actually going through your sample, because we're looking at a solid sample rather than a liquid sample, we have non-consistent samples with varying path lengths. And what that does is it causes scattering effects in your data, in the spectra that come out of that. And so you need to know how to adjust for that so that you can actually get your real information and that you're not basing some of your information on the fact that there's scattering. A very common way that we collect near-IR data is diffuse reflectance. It's a little bit similar to your diffuse transmission, except you're collecting that back scatter. And with diffuse reflectance, what happens is the light actually goes into your particles and it bounces around, and some of it takes different path lengths and comes out. So if you have larger particles, you have longer path lengths and therefore more interactions with the light, and you can have more scattering. So larger particles scatter more than smaller particles. And these are wavelength dependent. We don't really need to talk about this. It's just the relationship between absorbance and your concentration. So because our absorbance is wavelength dependent, dispersive elements can allow the lights at different wavelengths to be determined, right? We do our best to keep that path length constant. Solutions of similar concentrations should be similar. Now, it does get tricky when you get into solid data. As I said, you have more issues with that scattering. Okay? So, how do we start looking at this? If we take a look at our line plot of our data, we can see very quickly some additive baseline shifts. These are due to consistent scattering that is not wavelength dependent. And you'll see that your spectra look pretty much all the same, just offset from each other. When we do our descriptive statistics and look at our scatter plot, which I'll show a real live example in a minute, what you'll see is that all of the samples have the same slope, and they're just offset from each other. And this tells us that we have additive baseline effects, and so we need to apply pre-processing that takes care of those. Multiplicative scatter effects, this is going to be really important when you're dealing with particles that are wavelength dependent. Also, ATR can have different path lengths depending on your wavelength. And what you'll see is a general shape that is similar in all of your spectra, but that offset that I was talking about, there's a slope that's different. So some of the offset is higher at the higher wavelengths and some is lower at the lower wavelengths. And when you do your scatter plot, what you'll see is this fanning effect. This is pretty key that you have multiplicative effects. In the unscrambler, of course, we have lots of types of pretreatments that are in there. That top box with smoothing, normalize, baseline, those are the ones we use the most often. The next box is your more complex spectroscopic type pretreatments. If you are collecting in transmission mode, you can convert to absorbance mode, same thing with reflectance. We also have an ATR correction. That's all under the spectroscopic as well. So let me go through my example. So what I have here is some wheat data. So this is near infrared of wheat, different wheats, and eventually what we were wanting to do is measure the protein. So like I said, the first thing we're going to do is plot our data. So I'm just going to look at the calibration set, near IR. Okay. Now this is actually very common, what you will see with near-infrared data, especially something as complex as an environmental or agricultural sample, because you've got lots of things going on here, right? And the sample themselves are very inconsistent in this particular case. So that's why we see so much scattering and offsets going on here. So when I see something like this, I know immediately I'm going to have to do some sort of pre-processing and probably going to include at least some sort of baseline effect. So if we go to our data matrix, under tasks, then analyze, we can do descriptive statistics. Again, we're going to choose our calibration and our near IR spectra. Now what this shows is these are box plots. Each individual variable is going to be shown. So the line here is your median value. To this edge of the box, that's going to be your 25% value, and the top of the box is a 75% value of the entire range. And then this is going to be your minimum and your maximum. This just gives you a very overall idea of what your data looks like, how things are changing. As we can see, it looks like it's pretty consistent across the wavelength ranges. Each individual wavelength is varying about the same amount. So we're not really seeing any chemical effects here. If you're seeing chemical effects, you might see something where you have a lot that has very small changes and then a particular region has large changes in them. Now what I'm going to do is right-click in this box plot area, and under statistics, we have this thing called scatter effects. Now what this does is it looks at the group of samples that you're looking at, calculates the mean through each individual variable, and then plots each sample variable by variable versus the mean of that variable. Okay? And what we can see here, again, is a very straight line of the data points. This is telling me there's no real chemical effects going on. If there were a chemical effect happening, we would see some kind of swirls and swoops. It wouldn't be a straight line. Now that's all fine and good, but what we really want to look at is all of our samples together. So at the top here, we can choose our samples, and if we scroll to the bottom, we can do all. Now this is the scattering effect of every single sample that we're looking at. And what we see is the major influence here is that we have an additive effect. There's something going on across the entire wavelength range that is consistent. So what this tells me is I need to do something that removes additive effects. One of those, which is very common to use in near infrared, is going to be a second derivative. Now that will get rid of both your linear baseline effects and any sloping that is occurring underneath there. So I'm going to go back to my original data. Under tasks, we can do transform, derivative. I'm going to do a Savinsky-Goulet that has a smoothing involved with it as well. We're just going to do this over the calibration samples and the near IR spectra. I'm going to choose my second derivative. And this is something that's really handy in the unscrambler. What we can do is preview our results. So we can see what's going to happen when we apply this derivative before we actually apply it. So it allows you to make smart choices about what you're doing. You can tell whether it's improving or unimproving your data. All right, so we need to choose a number of smoothing points. And what you see here is we've got 3 smoothing points. If you look at this, it's still pretty noisy, though it has compacted our data a little bit. So I'm just going to go through here, and I just keep adding until it looks like I've gotten all of the major noise out, but I'm not losing my information. Okay, so I'm going to go with a total of 15 smoothing points, and we're going to say OK. Now, it's always good when you do any sort of transformations is to make sure that the label makes sense to you. In this case, we have wheat, and it automatically calls it an escalé, so I know that I've done a derivative, but it doesn't tell me what kind. So often what I'll do is right-click, and I will rename this, and I will say that it was a first derivative and 15 points smoothing, just so I can remember, because you never know when you open up this project 3 months from now and you've been looking at lots of other things, it's hard to remember what you've done. If for some reason you didn't name it something that makes sense, you can always look at your metadata, your information down here. It does tell you what transforms you've applied and gives you all the information about that. So it shows you the derivative order 2, polynomial 2, how many points you used, and what columns, what range you did that on. So if you had done a smaller sample, for example. Again, after I do this, I always plot. So let's look at our line plot. Now we have some data that looks like there's actually information in it. Okay. One thing we can do, just to kind of take a look, is if we right-click in here, we can do sample grouping. And remember I said we're actually interested in looking at how our protein is changing. So what we can do is come and define our protein range. We're going to create row sets from that. And now we're going to color code based on the protein contents. So we can see there's a little bit of a trend, right? So blue is going to be your lowest amount, red's your next highest, green's in the middle, and then these are the highest. But there's still a good bit of overlap of those data here. So again, what I'm going to do is do my tasks, analyze, look at the descriptive statistics, see if there's anything I might have missed. And so now you can see again, so you can see that there's not as much change that's happening down around 862, 870, but in the middle here around 950, that's where you're seeing the maximum amount of changes in your spectra. We're going to look at our scatter effects again. Go down and all. And now what you see, it's more subtle, and this is why we didn't see it before, because the additive effects were much greater than your multiplicative effects, but we do see this fanning. This is very typical when you have those types of wavelength-dependent scattering effects. So this is telling me that I probably want to apply something that's going to take care of that. In this case, we're going to do a standard normal variate. I need to make sure that I click the data that I applied the escalate to as first. I'm going to do tasks, transform, SNV. Again, if you want, we can preview, look at that, see how it's going to change it, and you see it tightens that information down, so you're losing a lot of noise there. Depending on your application, you need to be aware of whether you want to remove that variation or not. If, for example, I was looking at something and cared about particle size, these multiplicative scatter effects are usually very indicative of particle size. So if you're interested in particle size, you probably don't want to apply this kind of transformation, right? But in this case, we want to minimize particle size effects. So we're going to say OK. Take a quick look. So we have hot buttons at the top if you like to use those to plot our line plots. Take a look at that. And then again, I'm going to do my sample grouping just to take a look. And there's a good bit of overlap, but you can see there are some spectral differences that are happening through your different groups. So at this point, what I'm going to do is I'm actually going to do an analysis. So under Tasks, Analyze, I'm going to do a PLS regression. And I'm going to use my calibration data set, my NIR spectra, to look at my protein content. And this is my results. Just going to change some defaults here. Now what we see right away, the first thing we want to look at is our explain variance to get an idea of how many principal components or factors we want to use. In this case, I would say 3 factors. The 3 factors explains 89% of your data. If you notice in our predicted versus reference and our regression coefficients, the unscrambler suggests 4 factors. So that's just showing that this number with 4 factors is a little bit better in the numbers, and the RMSEs are a little bit better. But if you actually look at the difference between factor 3 and factor 4, you're not getting enough extra information from that factor to really justify including it. The fewer factors that you can use to explain your data or to do your prediction, the more robust your model is going to be in the future. When you start putting in things that look different, it's not going to be affected by that. And I'll show you some more tricks on how to figure that out. So once I've looked at that, I'm going to go to my regression coefficients here. What I'm going to do is right-click, PLS, and I want to look at the loadings. So I'm going to do that in line. All right, so now we have factor 1, and it looks like factor 1 explains 47% of our X data and 52% of our Y data. So that's pretty good. About half of the variation in our variables, in our X variables, in our spectra, are explaining the change in the protein, 52%. We can look at factor 2. Now we've got 25% is explaining another 30% almost of our data. And you see it still looks like a spectrum, and we could go and analyze that if we knew more about wheat. Factor 3 is getting a little bit, it's only explaining about 8%, and factor 4 only explains 1%. So that's another clue that we would only want to use 3 factors. Now, one little trick is I like to look at my loadings on top of each other to see how they relate. So I'm going to, just for fun, I'm going to look at actually the first 4 factors. If we go up here, you could choose the individual factors, look at all at once, or if you type in here, you can choose a range of factors that you want. So I'm going to do 1 to 4. Okay. And now we can see how they compare to each other. None of them look very noisy, which is fine, so you can justify using them. One thing that's nice to look at too is up here, right next to where we chose our factors, is what we call a correlation loadings. This puts it on a scale to show which are your important factors. If it's between this 0.7 and 1, then it's an important variable in that particular factor, and it's explaining your Y data. As we can see here, factors 1 through 3 all have areas that are up in these extreme areas that have important information in them, and you can see factor 4 actually falls totally in the middle, so it really doesn't give us any information. This is just another way to confirm to yourself that you don't want to use factor 4. And we can just look at those factors. Okay, now what we see here, if we now look at our predicted versus reference, this is a pretty good, even at 3 factors, we have an R-squared variable of 0.89. Anything that's very close to 0.9 tends to be pretty good, and considering this is an agricultural type sample, that's really, really good. You might be happy with, say, 0.75 even with an agricultural sample. We also want to look at our RMSEEs. This is the error in our prediction. Keep in mind that these values, these are not percentage values. These are actually in the original units, right? So this is in the protein amount. Okay, so I like to take a look at this and say, okay, I have a RMSE-CV of 0.517, and I'm just going to go from the center of the data. So our center of our data, our protein level is 11. I'm going to divide that. So it looks like we're around a 5% error in the center point of our data. That's usually pretty acceptable for almost all applications, even in the pharmaceutical world. So if you have questions, go ahead and type them up into the questions area, and I'll get to them at the end, or if I can, as we're going along. All right. So if we look here, I don't see really any gross outliers. We can do some look at that. If we right-click in here, we can look at our residuals and influence plots. We do have a lot of extreme values. So what we're looking at here, this is our hoteling t-squared. So along the x value, this is telling you how close to the center of the data, of the model, does each individual sample lie. On our F residuals is going to be how similar the spectrum, each individual spectrum is. Now, if we have anything up in this upper right-hand quadrant, those would be considered outliers, definitive outliers, because they both are very far from the center of the model, and their spectra look very different from each other. So you can justify taking those out. And you can always change the limits on this. You can make it more conservative or less conservative as to whether they're included or not. All right. I often look at the Q residuals. The Q residuals are the F residuals that are divided by the number of points that we have. And we see if we look at our Q residuals, there are some outliers. What we can do is mark them with a rectangle. I'm just going to go in this area. I missed one. All right. Now, if we go back to our regression overview, it will mark those individual samples along here. And you can see they don't fall very tightly on our regression lines. Okay. We can always go in and right-click, recalculate without those marked samples. And we can see if that makes our thing a little better. It's actually a little bit worse in this case. So sometimes those extreme samples help, and sometimes they don't. So you just kind of play around with it. So we're going to go back to our original model there. Okay, I have a questions about the loadings. The pre-processed spectra start and end with zeros due to the filter. That is true. So it starts with zeros here because we did our derivatives, and it has the ends on there. So you can see that they're actually very close to zero. They're not going to affect your data very much. If you want to, what you can go in and you can take those out. We can mark them here. Let me get my pointer back. Right, so basically what I'm doing here is taking out these edges that are zeros. And I'm going to unmark my samples for the moment. If we recalculate without marked variables, there's really no impact to the model, as you can see. Okay, so that's something to be careful. Sorry. So we want to understand what is the meaning of the negative and positive value of the factor and how it relates to the scores plot. Okay, so let me pull up the factors here again. Okay, so what's we need to keep in mind that when you run a PLS regression, there's a sign, an arbitrary sign assigned to the direction, okay? So when you have a positive loading here for your factor 1, what we can say is everything that is positively correlated are correlated with each other, right? So your wavelength ranges at, say, 968 and 920 are positively correlated with each other, okay? And they are negatively correlated with, say, at 1020, all right? And what this is going to say is that if we look along factor 1, okay, so that's going to be our, this direction. Oh, let me get right, this is factor 1 is going this way. Okay, so if something has in the scores plot, if it has a high value on factor 1, it means that it's going to have a high value here, and a high value here, and a very negative value here. Okay? If it has a low value on your factor 1 in your scores plot, it's going to say that it's going to have a lower value from these positively correlated loadings and a higher value in the negatively correlated loadings. Okay? So now what we're going to do is, we always say the proof is in the pudding, right? So it's great that we can analyze our data and create this beautiful regression model, but it doesn't mean much if you can't predict with it. Now, if you'll remember, the unscrambler wanted to default to using 4 factors, but we determined that we actually want to use 3 factors only. For using this in the future so that you don't have to go in and manually adjust it every time, if we go to our navigation pane in the left-hand side, find the model you want to use, right-click, there is an option to set your components. What we're going to do is it's defaulted to 4. We want to change that. We're going to make that 3, and we're going to say OK. And now anytime you apply this model, it will default to using 3 factors. Now I want to go back and predict this on my validation set. So we go back to our original data. Keep in mind that in the unscrambler, the pre-processing that is done is attached to the model, right? And so what you want to do is go back to your original raw data when you're doing predictions, rather than you don't want to do your predictions on pre-transformed data because it will double apply transforms. So we go to tasks, predict, regression. We want that second model where we took out those edges that were zeros. It has 3 components. We're going to choose our validation set, near IR, and we do have some reference values, so we're going to go and look at our protein. Now, if you want to check the pretreatment that is associated with this model, if you haven't labeled it as such, we can click on the pretreatment, and you can, see which pretreatments have been done over what range. So there's a lot of ways to keep track of what you've done in the past. We're going to say OK. And this is what our output is. So if we look at our crosshairs, the crosshair is going to be what our predicted value is. The deviation is this box that's around it. The tighter that box is to the center, the more confident we are in that data. It's basically like a confidence interval around your data points, your prediction. And what that's based on is it looks at how similar those samples are to your original data set, to your calibration data. Once we're in here, we can right-click under Prediction, Predicted with Deviation. We want to look at Predicted versus Reference. This is where we can get our really strong values, look at our regression lines, how close to 1 it is. This is pretty good. We have an R-squared. This is an interesting case where our validation set actually has a little less variation in it than the calibration set. As you see, our error is 0.4, which if we go back, we can see is a little bit lower than our error in our calibration data set. That's unusual, but it's not necessarily a cause to worry, just so you know. But typically you'll have a higher value there. But the closer that RMSE EP is to your RMSE CV, the more accurate your model is. Okay. Now you need to keep in mind that you can't predict any better than what your standard laboratory measurement is. So you need to know before you go into a project what sort of error you are okay with. And that's how you know when you can stop manipulating your data. So that is pretty much all I have for you guys today. I'm just going to go over real quick on a summary of how you go about looking at your data. You can keep this in kit for the future. We always import our data. I already had this set up, right? But make sure you inspect and plot your raw data. Look at your statistics. Look at your line plots, histograms of your variables. Let me show you that real quick. One thing you do want to look at is, say, our protein data. We might want to do a histogram of those to see what shape that it makes. Now, this is actually what you don't often want to see because what this is telling us is that we have a lot of samples that are in the center of our data, but not very much on the edges. So what can happen is if one of these edge samples is extreme, it can really pull your model to itself more so than if one of your protein levels of 10 are, because you have many more that are affecting that. What you really want to see in a histogram like this, when you're looking at your predicted value, is a boxcar. So this is a way of going in. It's like, oh, maybe I want to add some more data points that will have some lower values and some higher values. Or I'll remove some of the center ones to make it a little bit more even across. And you would also want to look at your validation set as well. Protein. And again, we've got this kind of extreme, this is actually a little bit of a skewed data set, so it's skewed to the right. Okay, so these are all things that you do before you even do any sort of multivariate analysis. So keep that in mind. We often do a principal components analysis on your spectra and your reference variables. I didn't do that in this case because I know I had a good data set, but that's something that you might want to do. It helps you identify any extreme outliers that are in your X data. If you had some particularly noisy data that you couldn't see visually in your line plots, you might see it in your principal components analysis. And then you want to have your calibration and validation data sets, decide on your pretreatment, optimize your model, determine how many components you want to use, determine if you want to choose a specific wavelength selection, and then you're going to validate, interpret your final model, and then you use it to predict new samples. And keep in mind that once you build a model, it's not a static entity. It has a life cycle. Depending on your process, you may want to reevaluate it in 3 months. You may find that it stays stable for a long time, and you only recheck it every year or so. So that's something that you need to think about in your plan when you implement these things. So thank you very much for joining me today. I will take any other questions. We still have a few more minutes to use. I have a question. If you have data set values outside near IR, for example, SWIR, I'm not exactly sure what that is, should this region be analyzed separately? That's going to be a case-by-case thing, you know. So you might have near-infrared and mid-infrared together, or say all the way into the UV visible. Sometimes you do different pre-processes. So you can do pre-processing just on specific ranges. Shortwave infrared, thank you very much. So yeah, so that's going to be closer to your visible range. And you can include them. You know, try it both ways and see what really works. How do you choose X variables? Okay, so when we are in here, let me get this one, line. All right. Yes, so if, for example, I knew some more about this data and I didn't want to use the entire wavelength range here, what you can do is figure out which wavelength ranges. Let's go back to our loadings. You might think that only this particular wavelength is the most important one. So what we can go in is select those wavelength ranges. And we can recalculate with the unmarked downweighted. Okay? and see if it does a better job. In this case, it really doesn't. I would need to bring up a different data set for that. Let me see what I have. Let's see. Cross-validation question. I have hierarchical data, stock solutions, dilutions over concentration range. Yes, so we're asking about different types of cross-validations. So when we go in here, there is a tab here for validation. You can choose very different kinds of cross-validations. I used random in this case. The most you can also do full. Full would be a leave one out, you may have heard before. You don't want to use that indiscriminately. If you have more than, say, 30 to 45 samples, definitely at least use random, don't use your full. But yeah, you can do a systematic approach where if you have certain repeats or you have batches and you want to leave out an individual batch at a time, you can do that as well. So there's different systematic ways that you can do cross-validation. Oh, it's asking how I chose the validation set. So in this case, I had it pre-set up, but I have a lot of data here. We have 523 data set samples. And so what you can do is you can actually automatically choose them sort of randomly. I go in sometimes and you usually use about 2/3 of your data as your calibration set and about 1/3 as your validation set. How you choose that validation set is going to be very dependent on your application. For example, in the pharmaceutical world, you actually have to use entirely separate data. It's very independent data. If you take data from the same batch, you can't use it in both your calibration and your validation set. But in other areas, you can. So there's different approaches to that. It's kind of outside the realm of this particular webinar, though. Does the Scrambler have any feature to help automatically selecting the optimal wave number range? Yes. When you do your regression, under validation, there's something called the uncertainty test. If we click that, you will see that it automatically highlights certain ranges. I don't know what that one is. Let me go back here. So here, it automatically selects certain wavelength ranges. What that does is it looks at, if we go here to important variables, it looks at the individual wavelengths. Oh, I'm in the wrong one again. Hang on. Sorry, guys. It looks at each variable and how it's changing in comparison with your Y value and what that variation is, okay? So in this case, these samples are changing significantly with our Y variable, but the variation there stays on one side of 0. If that variation crosses 0, then it's saying that sometimes the loading is going positive as you're increasing in protein, and sometimes it's going negative as you're increasing protein. So it's not considered an important variable. So that is one way to help you choose. Again, you have to make your own decisions yourself. Don't let Chemometrics be a black box. Okay? How do you compare your RMSEPs to typical measures of precision for your reference method? Okay, so that's, again, when you go into your into your analysis, you need to know what your standard laboratory error is, right? You're going to have some sort of error in your standard method, whether that's an HPLC or some other type of extraction method or gravimetric, okay? And so they're going to be in the same format, right? So remember your RMSEPs are in the same units as your original data. So that's how you can compare your measures of precision. I think that I have answered all the questions that have come at me so far. If not, please shoot me an email at hbrook, that's with an E, at chemo.com, and I'm happy to help you guys out. So thanks again for coming to our webinar on near-infrared data. Stay tuned for more webinars next year. Hope you all have a great